Hello everyone. In today's discussion, we discuss a very interesting question from the TIFR-CAM PhD entrance exam 2026, and this question is from the complex analysis part. In this question, here this set D is the upon unit disk in the complex number system C. Okay. And f is a holomorphic, means analytic function which maps from the domain D to the complex number set C, and this analytic function or holomorphic function satisfies this inequality: f of z modulus is greater than equal to square root of z mod. Okay, for all the z belongs to the open set D, and we have to check these following three statements. The first statement is saying that there exists a z naught belongs to G such that f of modulus of f of z naught is strictly less than 1, and second option is saying that there exists a z naught belongs to G, z naught belongs to D such that modulus of f of z naught is greater than equal to 1, and the third option is saying that the function f is bounded. We have to check these three things. Let us verify the option 1 and 2. Option and 1 and 2, the verification of the option 1 and option 2 are based on a very celebrated lemma. It is called the Schwarz lemma. Let us recall the statement of the Schwarz lemma. For the Schwarz lemma, if h is a holomorphic function which maps from the domain D to the complex number system C, here D is the upon unit disk, and it satisfies that h of 0 is equal to 0 and h modulus of h of z is less than equal to 1 for all z belongs to the upon unit disk D, then it says that modulus of h of z is less than equal to z mod for all z belongs to D. This is the statement of the Schwarz lemma. It will be used. Okay. This thing is clear that our f is also mapping from the domain D to C. Here h is mapping from domain D to C, but we have not this criteria that h of 0 is equal to 0. But here our f of 0 is saying that it is greater than equal to 0, but we need f of 0 should be equal to 0. So our f does not satisfy these two assumptions, this assumption and this assumption. So we have to construct an function h which satisfies these two things. So this will be our first target. Okay. But given that data is given that f of z modulus is greater than equal to square root of z mod. Okay, for all the z belongs to the upon unit disk. This implies what? This implies that if z is non-zero, then modulus of z is also non-zero, and that implies that modulus of f of z is also non-zero. This implies f of z is also non-zero. Okay, means if z is not 0, then f of z is also non-zero. Means if z belongs to this set upon unit disk difference 0, then f of z is not a 0 quantity. Okay, so this expression is well defined. So we can divide here on the both sides and by f of z, then we will get this quantity is less than equal to 1, but this is true on this set D difference 0. Okay, so here if you look at this expression, one can think that this function is satisfying that its modulus is less than equal to 1, which is one of the requirements of the Schwarz lemma. But this function does not guarantee that h of 0 is equal to also 0. Means this at the point 0, this quantity can also be non-zero. We are not getting that thing that this quantity is also 0 at the point 0. Okay, so to ensure that thing, we will define this type of h function, but in a slightly different way. Instead of square root of z mod, we are taking z mod or z. Okay, then we will define this function, and this function, the intuition of this function is coming this function to ensure that h of 0 is equal to also 0. Okay, this function will ensure that h of 0 is equal to 0. How? Let us estimate this function. modulus of h of z, and we are defining this function on this set because this expression is valid on this set. Why? Because there is a chances of that f of z also can be 0, but we have previously ensured that on this set f of z is never vanishing this one from 1. Okay, so clearly h is an analytic function because z is an analytic function and f of z is an analytic function, and f of z is non-zero on this set. So h is an analytic function or holomorphic function, but on this set only. We are not claiming it on the whole domain D. We are saying that this punctured disk, it is called the punctured disk, means this disk we are excluding the point 0. Okay, on this domain h is a holomorphic function. Okay, and now we will estimate the modulus of h of z. This gives this one, and this expression can be rewritten in this form. Here this term we know that it is less than equal to 1 on this set d difference 0 from equation 1. So this implies this thing, and from this we can guess that if h1 here there are two possibilities. Two possibilities means that I am saying that at the point z is equal to 0, it can be either a regular point or a singular point. These two are possible. If it is a regular point, means it if h is also differentiable at the point z is equal to 0, then we can take the limit on differentiability imply what? Continuity. Then we can take the limit on the both sides. Then by that sandwich theorem, it gives h of 0 is equal to 0. So there is no problem to ensure this thing, this requirement also. Clearly our h of z modulus is less than equal to 1 because z mod is less than equal to 1. This is already coming, but if z is equal to 0 is a regular point, we are getting h of 0 is equal to j0. But we know that our h is analytic on this whole domain, means this is the domain excluding the point z is equal to 0. On all these points our h is analytic, but at the point 0 we are checking that whether it is analytic or not. Okay, if it is analytic, then we are getting that h of 0 is equal to 0 by taking limit on the both sides. Okay, so there is no problem. But at the point z is equal to 0, if it is a singularity, then it can be what type of singularity? Because around all this point it is analytic, so z is equal to 0 is an isolated point, so it can be at most isolated singularity. Okay, I hope up to this point every argument is clear to you. Now I will ensure that but there are three possibilities. If f is an isolated singularity means what? It can be a pole, it can be a one is pole, another one is the removable, and the third one is the essential, essential. But if you look at this expression equation 2, if you take the limit z tends to 0 on both sides, it gives what? It gives a limit z tends to 0 of z is equal to means I am saying that if you look at the expression equation 2, if you take the limit z tends to 0 on both sides of the equation 2, it gives this thing, limit z tends to 0 modulus of h of z is equal to 0, means this limit exists and it is equal to 0. But for the pole the limit should be infinite, and for the essential singularity the limit does not exist. But in this case this limit value this limit exists and it is equal to 0, which is also finite quantity. So pole and essential are not possible. Okay, so the only possibility is the removable singularity, means we are getting that either z is equal to 0 is a regular point, or if it is a singular point, then it is a removable singularity. Okay, if it is a regular point, then we are done that h of 0 is equal to 0, which is our requirement to apply the Schwarz lemma. If it is not a regular point, then this limit value is 0. It ensures that it is a removable singularity. So if we can redefine the function h, that such that z by f of z on this domain, and it is 0 at the point z is equal to 0, then our function is a holomorphic function with that this thing and these two things. H of modulus of h of z is less than equal to 1 and h of 0 is equal to 0. So our required function h satisfies these two things. Okay. So by the Schwarz lemma, this implies that modulus of h of z is less than equal to modulus of z for all the z belongs to D. So in the particular case, this relation will hold on this punctured disk. Okay. This implies f of z modulus is greater than equal to 1 on this punctured disk. Then by using the continuity, means we are getting that our f of z is greater than equal to 1, but excluding the point z is equal to 0. Now I will take the limit, since our f is analytic, so it is also continuous at the point z is equal to 0, means our so if we take the limit on both sides, limit z tends to 0, f of z, we will get f of 0 modulus greater than equal to 1. If we merge these equation 3 and 4, we will get that f of z is greater than equal to 1 for all the z belongs to D. So this is happening. Okay. Means our function f of z is always greater than equal to 1, modulus of f of z is always greater than equal to 1 for all the z belongs to D. We are getting these things, means f of z is greater than equal to 1 for all z belongs to D. This is true. So this is which one? This one is false, because it is saying that f of z, there exists a z naught, because we are finding that our f of z is always greater than equal to 1 for all the z, so it cannot be strictly less than 1, and this is true, there exist, but we are getting all the points, but it is also true, they all, means for the particular point is also true. Okay. Now we have to check the option 3, whether f is bounded or not, but this thing does not imply the f is unbounded or it is also bounded. We cannot infer from this that f is bounded or unbounded. But we can create a counter example such that f is unbounded. The required counter example is given here. This one. If one can consider this function clearly, when z approaches to 1, this function will blow up to infinite. Okay, so it is an unbounded function, but we have to ensure that this function is analytic. Okay. Clearly 2 is analytic and 1 minus z is analytic, and 1 minus z does not equal to 0 on D, because D contains all the points where z mod is strictly less than 1, so it cannot be 0 because z is not equal to 1 on D. Okay, so therefore the numerator is analytic and denominator is analytic, so f of z is analytic on D. There is no problem on the analyticity. Next we have to verify that f of z modulus is greater than equal to z mod, square root of z mod. Okay, so we have to verify this thing, and this can be verified in this way, because 1 minus z mod is less than equal to by 1 plus z mod by the triangle inequality, and this is less than equal to 2 because z mod is less than equal to 1. This quantity is less than equal to 1, so 1 plus 1 gives 2 on the domain D. This implies what? 1 upon 1 minus z mod is greater than equal to 1 by 2 on the set D. This implies that 2 upon 1 minus z mod is greater than equal to 1, and this is greater than equal to square root of z mod, because z mod is less than equal to 1. Okay, this implies this thing, so this is our required inequality. So our function, and this is our f mod, fz mod. Okay, so our function, required function f is satisfying this criteria and it is analytic function, but at the point z is equal to 1 it is infinite, so when z approaches to 1 it goes to this modulus goes to infinite, because z is equal to 1 is a pole. So therefore our function f is an unbounded function. Therefore option 3 is false, because option 3 is saying that f is a bounded. So option 3 is false. So let us check the options. Only 1 is true, it is false. Only 2 is true, yes, it is true. Only 1 and 2 are true, this is false. Only 2 and 3, this is true, this is also false. So only the option B is true. I hope that you all understood it very well. Thank you again.